Good evening, guys. Hope you're doing well. I'm assuming you're watching this in the evening, or if you forgot to and woke up super early to watch it, good morning. Jokes on you. So today we'll talk about rational functions, and it's going to be a two-day class, a two-day lesson, but hopefully we can cover it in one. A rational function is simply an expression or a function that can be written as a quotient of two polynomial functions. So it's a quotient in that you have a numerator and a denominator, and the items in the numerator and denominator are both polynomial functions. So that's simply what a rational function is. In rational functions, you have something called a vertical asymptote. Now, last year and also in 9th grade, we kind of touched on asymptotes a little bit. If you have a graph and you have a certain line where the graph gets closer and closer to that line but never touches it, this could look like this too, gets closer and closer to the line but never touches it, then that line, so in this case this y-axis, is called a vertical asymptote. So this is called a vertical asymptote, right? On this vertical asymptote, the graph gets closer and closer, but it never touches it. So the nature of this is that as x tends to positive infinity, then you can see that the y value is getting closer and closer to 0. And as x tends to 0, because you can see here I'm getting closer and closer to 0 from the left, as x tends to 0 from the left, then the y value is getting closer and closer to negative infinity. So this is called a vertical asymptote. It's a vertical line, x equals a, so a can be any value really. A can even be here, and on that graph, let me use a different color. On that graph, the shape of the curve will look like this, and the shape of the curve can look like this, because it's simply saying that as you get closer and closer to this red line, the graph approaches infinity, never touches but gets closer and closer to the graph. That's what an asymptote is. So it's telling you that if this is a, this is the a value, this is what this definition is telling us. If the vertical line x equals a, where the graph tends towards positive or negative infinity as the input approaches a. As the input value gets closer and closer to a, as the x value gets closer and closer to a, the graph tends to positive infinity. As the input value gets closer and closer to a, on this side, as you get closer and closer to a, this is getting further away, but as you get closer and closer and closer and closer to a, then y tends to negative infinity. So that's a vertical asymptote. How do we find vertical asymptotes? Vertical asymptotes happen at points where the graph is undefined. And remember, for something to be undefined, then I need to be dividing by 0, because division by 0 is undefined. And what this shape here means is that this graph cannot have a value, this function cannot have an output value when the input value is a, because for this input value a, the function is undefined. So I'm simply trying to look for the values for which this function is undefined. And since I know that to get undefined I divide by 0, then that means that the denominator of this function has to equal 0 for the function to be undefined. So what we do when we're finding vertical asymptotes is simply equate the denominator to 0, because when the denominator is equal to 0, that function is undefined. So here I'm going to try and factorize this. The factors are x and x of x squared. The factors of 21 that combine to give me 4 can be 7 and 3, and that 7 has to be a positive, the 3 is a negative. Then I combine them to get x minus 3, x plus 7, because I got this way and that way. And remember, you can use any of the methods of factorization that you like to use or that you prefer to use is equal to 0, or if you're too lazy you can just graph it, find the zeros. You can just graph this and find the zeros. So when I solve for this, I can see that x is equal to 3 and x is equal to negative 7. These two values, if I substituted them into the equation of this function, would give me 0 in the denominator, and therefore would show that the function is undefined at those two values. What that means is that x equals 3 and x equals negative 7 are the vertical the vertical spelling asymptotes of this function. So to get vertical asymptotes, simply set the denominator equal to 0. This word is denominator, Mikhail. I know you're wondering. This word is denominator. So you set the denominator equal to 0 to find the vertical asymptotes. On graphs, there's also something called a removable discontinuity. So a denominator, the removable discontinuity, or a hole, I'm just going to call them holes, is a denominator restriction from the original function, which is no longer restricted in the reduced function. What does that mean? You could have a function that is, say, x plus 2, x plus 3, divided by, this is after factorizing it, x plus 2, x plus 1. Now, as you can see, these two factors are the same, so naturally I'm going to be inclined to cross them out, so that the reduced expression is x plus 3 out of x plus 1. Now, the only problem with this is that I'm forgetting that if I put a value of x is equal to 2 in this function, it will be undefined, because x equals 2 gives me a 0 in the denominator, which is undefined. So that simply means that at that singular value, x equals negative 2, x equals negative 2, at that value, the function does not have an output. But then after that value and before that value, the function will have outputs. So that value would technically be called a hole, or a removable discontinuity. So it's simply a denominator restriction, going again from the original function, which is no longer restricted in the reduced function. This is the reduced function. It is not restricted, but it was restricted in the original function. So that's what a hole is. A horizontal asymptote is a line y equals b, where the graph approaches the line as the inputs go from positive to negative infinity. I think I showed you this a little bit earlier, but I'll show you again. So the function, the output of this graph approaches 0. I hope you can see that the function is approaching 0, and here the function is approaching this side. The function is approaching 0 as x tends to positive or negative infinity. So as x tends to negative infinity, then the function is going to 0. And as x goes higher, going away from, higher and higher to positive infinity, the function is still approaching 0. That's a horizontal asymptote. Remember, vertical asymptote was the opposite. As x approached this value a of the vertical asymptote, then the function tended to positive infinity, and the opposite here, as x approached this value a from the negative side, this is from the positive side, then the function went to negative infinity. So horizontal asymptote is this y value, y line, and the vertical asymptote is this x line. Let's see how we can find horizontal asymptotes. So remember, horizontal asymptote is that horizontal line for which the function is going to 0. So that means in order to find the horizontal asymptote, I just need to set the function equal to 0. So, but that's not what this is saying. This is saying if the degree of a numerator is smaller than the degree of the denominator, the horizontal asymptote will be at y is equal to 0. What this really means, because horizontal asymptote is I'm trying to figure out what's the behavior of this function as the x value goes very high or as the x value goes very low. One way mathematically to look at this is I can look for the biggest power in this rational function. The biggest power is x squared. Then if I decide to divide each term by x squared, I will not have changed the meaning. So if I decide to divide 4x out of x squared, 2 out of x squared, 3x squared out of x squared, 5x out of x squared, and 2 out of x squared, I have not changed the meaning, because let me just show you sidebar here. If I have 2 plus 3 out of 4, 2 plus 3 is 5 out of 4, let me just use a different number. 2 plus 3 out of 5, so 5 out of 5, I know the answer to that is 1. But what happens if I divide each of these numbers by, let me use a number that's that's going to be easier. Let's say 4 plus 2 out of 2, right? 4 plus 2 is 6, divided by 2 is 3. I know the answer to this is 3. What if I decide to divide each number by 2? If I divide 4 by 2, divide 2 by 2, divide by 2 by 2, each number in this rational in this fraction by 2, I will end up with 4 out of 2 is 2, 2 out of 1 is 1, and 2 out of 2 is 1, 2 out of 2 is 1. So the answer is still 3. Just showing you that dividing the biggest term through each of the terms of this rational function does not change the meaning, but it helps me to see what happens when the x value goes very high or goes very small. Now 4x out of x squared is the same thing as 4 out of x. 2 out of x squared, that remains 2 out of x squared. 3x out of x squared, 3x squared out of x squared is just 3, minus 5x out of x squared is just 5 out of x, and then this is 2 out of x squared. Now this can help me see, so for example, as x, if x is becoming a very big number, so going towards positive infinity, what is happening to f of x? Well, let's see. If x is a very big number, 4 divided by a very big number will be close to 0. 2 divided by a very big number will also be close to 0. This is just 3. 5 divided by a very big number will be close to 0. 2 divided by a very big number will also be going to 0, and I just end up saying that f of x is equal to 0, and f of x equals 0 is the same as y is equal to 0. So that's basically telling me that if the numerator, if the degree of the numerator is smaller than the degree of the denominator, then the horizontal asymptote will simply be at the line y is equal to 0. Now what I've done here, you don't have to divide each of the terms to come to this result. All you have to do is divide the first terms, the leading terms only. Just divide the leading terms by the highest power in the whole quotient, in the whole rational function. Alright, if the degree of the numerator is equal to the degree of the denominator, this is another type of horizontal asymptote. If the degrees are equal, then the horizontal asymptote will be at coefficient of largest term divided by coefficient of largest term in the denominator. So again, I'm going to use the same idea that I used before, dividing by the highest term, the highest power in the rational function. But as I showed you, I don't need to do it for all of them, because I'm trying to figure out the end behavior. I know that if I divide this, again it will just tend to 0, so I just need to do it for the first terms. So 4x squared divided by x squared and 2x squared divided by x squared. You can see that this x squared cancels out, and I just end up with 4 out of x squared cancels out of 2, which is just 2. So when the degrees are equal of the numerator and the denominator, all you have to do honestly is divide the 4 by the 2 without having to go through this. The 4 by the 2 to get y equals 2 as your vertical asymptote. Another type is called a slant asymptote or an oblique asymptote. It's not horizontal and it's not vertical. It's a slant. It can be a slant like that or a slant like that, of a positive or negative gradient. So this happens when the degree of the numerator is 1 more than the degree of the denominator. So when the degree of the numerator, as you can see here, is 1 more than the degree of the denominator. And remember, to figure this out, I just need to divide the coefficients by the largest term. So if I divide, I divide by the degree of the denominator. So if I divide 3x squared divided by x, which is the degree of the denominator, and I only need to do it for the first terms, then I'm going to end up with 3x. So that means that as x tends to a very big number, this whole expression will be 3x. This tells me that y is equal to 3x is my slant asymptote. What that looks like on a graph is this. So this is your slant asymptote. Y is equal to 3x. Wait, is it 3x plus 1 or 3x? Oh, sorry. For this one, I'm going to do it for all the terms such that I don't miss a factor. So I'm going to do it for all the terms because x is the same power as this. So I'm going to do it for all the terms. If I divide 3x squared divided by x minus 2x divided by x plus 1 divided by x, x divided by x minus 1 divided by x, then I ask myself what happens when x be first reduce it. This is 3x minus 2 plus 1 over x, all divided by 1 minus 1 over x. Then ask what happens when x becomes a very, very big number. Hope you can see that this goes to 0, this goes to 0, and you're only left with f of x is equal to 3x minus 2, which means that y is equal to 3x minus 2 is going to be your slant asymptote. It's going to be your slant asymptote. So here it should have been minus 2. It's just an error in naming. 3x minus 2. Yeah, alright, so a slant asymptote happens when the degree of the numerator is 1 more than the degree of the denominator. Right, we have an example where we try to bring everything together. Find the domain, vertical asymptotes, whole and horizontal asymptotes, or slant asymptotes of the function. If I look at this, since the degree of the numerator is less than the degree of the denominator by 1, I know for sure that the horizontal asymptote is going to be equal, and y is equal to 0. But before I get there, let me start with vertical asymptote. Remember, vertical asymptote is the point where the function is undefined, and if the function is undefined, I just need to set the denominator to 0. So to get the vertical asymptote, I set x minus 1 is equal to 0. This tells me that when x is equal to 1, the graph is undefined, and therefore this is my vertical asymptote. The holes, I'm not going to have any holes. I have a vertical asymptote. That's the only point where the graph is undefined. I will not have any holes because I don't have any factors that are going to cross out. So I don't have any holes. Horizontal or slant asymptote. Now, if you don't remember the rules for this asymptote, just go ahead and divide the leading degree of the denominator by each term in the function in the function. So if I divide this by x by x, if you don't remember, just go ahead and divide 1 by x, and then ask yourself, simplify 4 out of x, this is 1 minus 1 out of x. Then ask yourself what happens when x becomes a very big number. When x is a very big number, 4 divided by a very big number is 0. This is 1 minus 0, so that means f of x is just equal to 0. So the horizontal asymptote is just y is equal to 0. And remember, the rule was that if the degree of the numerator is less than the degree of the denominator, then this is the asymptote. But like I said, if you don't remember, you're welcome to divide by the highest power of the denominator each time. Slant asymptote, I don't have any because I have a horizontal asymptote. Now, a graph cannot have both a horizontal asymptote and a slanting asymptote. It only has either one of the two. And a graph cannot have more than one horizontal or slant asymptote. It either has, it only has one, and it only has either of the two. It can't have both. Hope you remember that. Just write it here. Can't have more than one horizontal asymptote. This word is can't, Mikhail. And it only has either horizontal asymptote or slant asymptote, but not both. Okay. Right. Another example: find the domain, vertical asymptotes, holes, and horizontal or slant asymptotes. The domain. Did this one ask for domain? Oh no, it asked for domain. Okay, I forgot to talk about domain. The domain of a rational function are all the real numbers or real values on a number line, except the vertical asymptotes or except the wholes. So the domain of this function is going to be all real numbers except, so it's going to be negative infinity except the vertical asymptote. Since the vertical asymptote is 1, it's going to be negative infinity and 1 include union 1 to positive infinity. So it's going to be all real numbers except the vertical asymptotes or the wholes. This one, x squared divided by, x out of x squared minus 9. If I simplify it, this is x minus 3 into x plus 3, completing squares, difference of squares, sorry, because this is 3 squared. I hope you remember that. Difference of squares says that if I have a squared minus b squared, that's going to be a minus b into a plus b, and I have x squared minus 3 squared, that should be x minus 3 into x plus 3. That's why I have that here. Alright, so domain, remember domain is all real numbers except for the vertical asymptotes. If you look at this, the vertical asymptotes are found by setting the denominator equals 0. So if I set the denominator equals 0, then I will get x is equal to 3 and x equals negative 3 as my vertical asymptotes. So that means that the domain is all real numbers, so starting all the way from negative infinity up to negative 3, then from negative 3 up to 3, including or union from 3 up to positive infinity. This does not include either of those values because they're not in the domain, but all other real numbers are part of the domain. Wholes, I don't have any wholes because I am dividing. I'm not crossing out any of the factors in the denominator and numerator. So these vertical asymptotes are also the wholes because they are the values of x at which the function is undefined. Horizontal or slant asymptotes. Now I know the rule is that if the degree of the numerator is less than the degree of the denominator, the horizontal asymptote, the graph has a horizontal asymptote, yes, and that horizontal asymptote is y equals 0. But like I said, if you don't remember that rule, you can just go and divide everything by the degree of the highest degree of the denominator. X squared over x squared, 9 over x squared, you will see that this reduces to 1 out of x, 1 out of x, and then 1 minus 9 out of x squared. And you can see that if x becomes a very big number, this whole thing will be 0, and this whole thing will be 1. So you just end up with y equals 0. Do I have a slant asymptote? No, because the power of the numerator is not bigger than the power of the denominator. So I found the domain, vertical asymptotes, wholes, and horizontal asymptotes of the function. Domain, vertical asymptote, wholes, horizontal asymptote, or slant asymptote. This power of the numerator is bigger than the power of the denominator, so I expect to have a slant asymptote. But let me start with vertical asymptotes. It's a good place to start. Vertical asymptote, set denominator equals 0. 3x minus 2 is equal to 0, so that means x equals 2/3. So that means that the domain is all real values excluding this value. So negative infinity to 2/3 union 2/3 to positive infinity. That's the domain. The vertical asymptotes, I've got that. The wholes, let's check if this is factorable. So 81x squared minus 18 is the same as, if I pull out a 9, I'll have 9x squared minus 2. Right, 9x squared minus 2 divided by 3x minus 2. Yeah, I'll factor that, but I don't see anything that I can cross out. 9 times 9, just checking my math, 9 times 9 is 81, 9 times 2 is 18, so I can't cross out anything. I wish this had been a 36, or yeah, 36, such that this would be a 4, in which case I would cancel out, but it's not, so I can't cancel out anything, so it's just staying like this. That means I don't have any holes. Checking for horizontal asymptotes or slant asymptotes. Again, since the power of the numerator is bigger than the power of the denominator, I expect to have a slant asymptote. How do I do that? Divide each term by the biggest power of the denominator. So 81x squared divided by x minus 18 out of x. And remember, you can use the rule, and the rule is that if this is the case, actually, yeah, this is what I'm doing. Then 3x out of x minus 2 out of x. See, this simplifies to 81x minus 18 out of x divided by 3 minus 2 out of x. So if I set x to be a very, very big number, this will be 0, this will be 0, and I'll just end up with 81x out of 3, which is 27x. So that means that that's the equation of my slant asymptote. So my horizontal asymptote, which does not exist because the power is bigger, is now a slant asymptote. Is, just put this back, the slant asymptote is y is equal to 27x. Yeah, so that's the information that this question asked for. Another one, domain, vertical asymptote, holes, horizontal asymptotes, or slant asymptotes. Okay, start with vertical asymptotes by setting denominator equals 0. Denominator equals 0. This factorizes to I'm setting it equals 0. If I factorize, if I take out 3x squared, I'll be left with x minus 2 equals 0. Now these are two brackets. If I set this bracket equals 0, I'll have x is equal to 0. Set this bracket equals 0, I'll have x equals 2. So those are my vertical asymptotes. Now checking for domain. Domain is all the vertical asymptotes. Sorry. Step 1 is supposed to be simplifying, sorry about that guys, simplifying the equation of this polynomial. And that's supposed to be step 1. When I look at it, 5x cubed plus 2x minus 1 divided by 3x cubed minus 6x squared, it doesn't look like something that's easily factorable. So I'm going to go ahead and assume that it can't be factored easily. You can use what we learned yesterday, remainder theorem, long division, synthetic division, to try and divide this, but I'm not going to go into that. I'm just going to go ahead and assume that it's not factorable because I don't see any clear factors. So going back to this, so I was safe to go this way. Going back to this, the domain is going to be all real values, negative infinity up to 0, union 0 up to 2, union 2 up to positive infinity. Since that's the domain, holes, do I have any holes? Since this wasn't factorable, so I didn't cancel out any common factors, then before I go there, just give me a second. Yeah, I'm right. Since I didn't cancel out any common factors, I don't have any holes. I only have vertical asymptotes. The horizontal or slant asymptote, since this power is equal to this power, the numerator power is equal to the denominator power. To find that asymptote, the horizontal asymptote, the rule says that I just need to divide this coefficient divided by that coefficient, so that the horizontal asymptote will just be 5 out of 3. Again, if you forgot the rule, just get this power divided by everything. Divide this power of the biggest power in the denominator by everything throughout. 5x cubed divided by x cubed plus these ones will all go to 0, you know that. 3x cubed divided by x cubed, this one will go to 0. So then you just end up with 5 out of 3, which is the same thing. Alright, so that has the horizontal asymptote, so I shouldn't expect any other slant asymptotes. Find the x and y intercepts of these fractional functions. Now the x and y intercept, their definition does not change whether or not you're dealing with rational functions or any other type of functions. At the x-intercept in all graphs, at the x-intercept, the y value is equal to 0. So I find the x-intercept by setting f of x, the whole f of x equals 0. So x plus 5 divided by x squared plus 4, if I set that equal to 0, cross multiply, I hope you can see that x plus 5 times 1 will be equal to 0 times x squared plus 4, which is still 0. So the x-intercept is just x equals to -5. Write it as point -5, 0. The y-intercept, again, the definition does not change. It's the value at which x equals 0. It's where the graph cuts the y-axis, and at that point the x value is equal to 0. So to find the y-intercept, I will just set x equals 0 in this equation. 0 plus 5, 0 plus 4. So the y-intercept is 5 out of 4, and as a point x is 0, y is 5 out of 4. So that's how you find x and y intercepts of rational functions. The local and end behavior of this function, you're trying to figure out what's happening as x goes to infinity or as y goes to infinity. So what I'm going to do first, the end behavior is you're trying to figure out what's happening as x goes up. And I mean, as x goes to positive and negative infinity, what's happening to the y value? Is it this kind of shape? Is it this kind of shape? Is it this kind of shape? Or is it this kind of shape? That's what you're trying to figure out. So I'm going to first check if this is factorable, and I can see if the numerator is factorable. If I factor the numerator, it's the same thing as x minus 1 into -3, -1, and x minus 3. Because the factors are -3, -1. The denominator is x minus 5 and x plus 1. You guys can check my factorization. So I don't have any factors that cancel out. Alright, that's useful. I see that since these are equal, the y asymptote, the horizontal asymptote is y equal to 0. The horizontal asymptote is y is equal to 0. And remember that at a horizontal asymptote, the behavior of a horizontal asymptote is that as x tends to infinity, the function tends to 0, right? And as x tends to negative infinity, same thing, the function tends to 0. Could even be up here or down here, but the function is going to go to 0. So the end behavior of f of x, this is telling me that since I have a horizontal asymptote, then that's what's going to happen at the end. Let me first check for vertical asymptotes also to get an idea of the end behavior. X minus 5, x plus 1, set that equal to 0 to get vertical asymptotes. That gives me x is 5 and x is -1. That tells me that at those points x is 5, which is over there, and x is -1, which is over there, that as x goes closer and closer to 5, the y value, as x goes closer and closer to 5, y is going to go, because look at this graph is expected to go this way, so then vertically it's going to be expected to this way. Y is going to go towards positive infinity. Or it could be the other way around, that as x tends to 5, y is going to negative infinity, like that. So the curve would be like that and like this. So y could be positive infinity or negative infinity. And as x tends to -1, same thing, you're going to have that kind of behavior or this kind of behavior. So generally, the end behavior of this curve, I'm going to be looking at the extremities. As x tends to negative infinity, what's happening to the function? It's going to 0. And as x tends to positive infinity, what's happening to the function? It's going to 0 as well. So that's my end behavior that's given to me by the horizontal asymptote. As x tends to negative infinity, the function tends to 0. and as x tends to positive infinity, the function tends to again 0. So just a summary of what the asymptotes were. A vertical asymptote is where the bottom equals 0, or just set the denominator equal to 0. If the degree of the top is and the degree of the bottom, the horizontal asymptote is at y equals 0. If the degrees are equal, to get the asymptote, the horizontal asymptote, divide the coefficients of the numerator and the denominator. If the degree of the top is 1 more than the degree of the bottom, then you have a slanting asymptote. If it is 2 or more bigger than the degree, then you don't have a horizontal asymptote, and you also don't have a slanting asymptote. So this is your homework. I hope you can enjoy